Okay, we're going to continue looking at hypothesis testing about a mean, but this time we're doing it under the situation in which sigma, the standard deviation of the population, is not known. The requirements for such a test: that it's a simple random sample, the value of the population, standard deviation sigma, is not known, and either the population is normally distributed or n, the number in the sample, is greater than 30. Our test statistic, the sample that is converted into a test statistic, which is a value used in making the decision about the null hypothesis, with the assumption the null hypothesis is true. And here really is the major difference from what we did last time. We're going to use Table 5 and find a t-score instead of Table 4 and finding a z-score. It'll still involve p-values and critical values, or even a confidence interval method, but really this is the one significant difference. We are looking at t-scores in Table 5. Now, got to caution you, the only difference between the equation we had last time and this one is the sample standard deviation instead of the population standard deviation. The other three numbers would be exactly the same. And so it's really easy to not catch that you might be actually calculating a z-score versus a t-score. The real question is, are you using the right table? So, let's look at the traditional method first. We have to make the symbolic form of the claim. We make the symbolic form of the counterclaim, or that the claim is false. H1 does not contain the equal sign. H0 does contain the equal sign. Even if the claim is made in such a way that it has the equal sign, we have to reword things so that it falls this way. Select alpha, which usually is given to us. Identify relevant statistics and determine the sampling distribution, which in this case means using Table 5 and finding the appropriate t-score. We find the test statistic, the critical values, and the critical region. We reject H0, the null hypothesis, if the test statistic is in the critical region, or fail to reject H0 if it is not. And then we restate in simple terms and address the original claim. Now, if we're doing the p-value method, most of the beginning steps are exactly the same as in the traditional, except once we get to the part for the test statistic, we would then turn that into a p-value, which could be compared with alpha. And as the book maintains, you can use the tdist function in Excel, and all you need is a little bit of information, like the degrees of freedom and n and so forth, and then you can go ahead and use that if you wanted to get more of an exact value than using a table. And then finally we have the confidence interval method, in which for two-tailed tests, the confidence interval with a confidence level of 1 minus alpha. For a one-tailed test, it's 1 minus 2 alpha. We reject the claim if the parameter is not included within the confidence interval. So what we're going to do is look at one potential problem, one example to test, one claim to test, and then see how each of the hypothesis methods would look. So first off, we have a sample of weights of 40 men. It has a mean, remember X bar is the mean, of 172.55 pounds, and S, the standard deviation of the sample, of 26.33 pounds. Sigma is not known. Use these results to test the claim that men have a mean greater than 166.3, which was what was used by the National Transportation and Safety Board. We're going to use alpha as 0.05. So first off, are the minimum requirements met? It is a simple random sample. Sigma is not known. And since n is 40, it is greater than 30, and we're okay. So we're going to start off with the traditional method. And let's go through the steps here. They're all listed out, but still I want to go through them all. So first off, the claim the mean, and again, we're using the sample to make a claim about the population. So it's not that X bar is greater than 166.3, it's that the mean of the population is greater than 166.3. Our counterclaim, notice that the counterclaim has less than or equal to. Okay, our null hypothesis, mu equals 166.3, and then the alternative, which matches the claim most of the time, mu is greater than the 166.3. Now, one thing I should mention before we go on, a lot of the problems in the book will write H0, the null hypothesis, as the counterclaim. The key is it's including the equal sign. So just keep that in mind and don't be confused by it. But some of the homework assignment problems from my math lab will want the less than or equal to or the greater than or equal to instead of just the equal sign. Alright, so our alpha is 5. Now we're going to calculate in step 6. This is really the only place we do our calculations in step 6. Here is our t-score equation. Plug in the numbers. So again, the mean from the sample. This is our claim, so this has to match our claim. This has to match our null hypothesis. So that's really, we're putting that in to test it. There's our standard deviation of the sample. Here's our n, and we come out with 1.501. And again, just to repeat, and that's why it's in here, this equation is almost identical to the z-score equation where sigma is known. The real difference is they use different tables. So you could have all the same numbers, basically calculate the same score, but you might call it a t-score instead of a z-score, or vice versa, and therefore we're using the wrong table. Alright, now, since we're doing the traditional method and we have our test statistic, we now need to turn our alpha into a critical region, and so 0.05 in the right tail, degrees of freedom is 39. That gives us a t-score of 1.685. So this one here is based on the alpha. Change the alpha, we would change this one. So that means the critical region is to the right of that t-score. Now, this is what we calculated from step 6. So since 1.501 is less than 1.685, in other words, it's not in the critical region, it's not beyond that score. Remember, basically the middle is the mean, that's 0, and so we're going to fail to reject the null hypothesis. We cannot reject the idea that the mean actually equals 166.3, where the claim was that it was greater than. And again, note that t equals 1.501 is closer to the middle than t equals 1.685. Restate, there is not sufficient evidence, and generally that's kind of the way you word it. There is either not sufficient evidence or there is sufficient evidence to support the claim that the population mean is blah blah blah, in this case greater than 166.3. In other words, the results of this sample could have happened just by chance. They're not indicative of any particular conclusion. And by the way, speaking of conclusions, we do not prove the null hypothesis. Okay, we just failed to reject it. Those are not the same thing. We just say we don't have the evidence to reject it. That does not mean that it's actually true. So that is the traditional method. Now let's look at a confidence interval method. And so really the major difference here is we're going to, instead of the test statistic that we were doing before, we're going to build our confidence interval. Okay, so it's the same 1.685 that we had before because it's still 0.05 in the right tail. That refers to a 90% confidence level. Remember that it's 1 minus 2 alpha, so 2 times that, 0.1. 1 minus 0.1 is 0.9, 90%. Since we're doing a confidence interval, we need our margin of error, where the margin of error is based, in this case, on the t-score, the critical value t-score. Plug in our numbers, and we get 7.015, which we can round to 7.02, because our mean was only 2 decimal places as well. So we go ahead and create our interval our mean should be between 165.53 and 179.57. Now, so all of that, that's just 6. That's just figuring out what the confidence interval was. Now that we've done that, we can make our judgment. Because the confidence interval includes 166.3, it's above 165, so it's in the interval, it's within that interval. And in fact, some values may actually be less than 166.3 and still be in the interval. We fail to reject the null hypothesis. So there is insufficient evidence to support the claim that mu has to be bigger than 166.3. So again, since it fell within the confidence interval, we had to fail to reject. If it fell outside of the confidence interval, then we could reject the null hypothesis. All right, we want to find p-values that are associated with this test statistic. And again, using Table 5, we have alpha 0.05 in the right tail. And then this is for the greater than case. H1 is mu is greater than 166.3. Our DF is 40 and all of that, just like we did before. And so we get that same 1.501. Okay, but now when we actually look at Table 5, what we see is that the 1.501, because remember in Table 5 it doesn't list every value. 1.501 is not there on the table. We got that from the test statistic. When we look at the table, what we see is for row 39, the degrees of freedom of 39, the 1.501 falls between 1.685 and between 1.304. This was with the column heading of 0.05 in one tail. This was with the column heading of 0.1 in one tail. So our p-value is between these two. It's between 0.05 and 0.1. Now, if we were to actually use Excel and use our t-score that we got from the test statistic and our degrees of freedom, 40 minus 1 is 39, and plug those in, Excel would tell us that the p-value was actually 0.0707, which, if you look at our range, 0.07 would fall between 0.05 and 0.1. So again, this one was calculated directly using Excel, given what the test statistic was and what the degrees of freedom is. Now, this last question is, based on this information, what would be the range of p-values? So doing very similar to what we did here. Here's our t-score, 4.408. Our n is 40 again. Our alpha is 0.05. Note, in this case, we have a mu not equal to 120 pounds. So that makes this two-tailed because of the not equal in our claim. So two-tailed, again, 39 for our degrees of freedom. T is 4.408. When we look at Table 5, and we can do a real quick look at Table 5 to just see what's going on here. Let me get it out so that you can see. Again, we're in row 39, and we're trying to look at 4.408. So if we go to row 39, okay, note all of these are less than 4.408. In fact, because of the pattern, 1.3, 1.6, up to 2.7, 4.408 would be out here somewhere. Well, what that means then, since 4.408 is bigger than the 2.708, then the p-value must be less than what's at the top of the column that had the 2.708. Well, that's actually 0.01, so our p-value has to be less than 0.01 because we're to the right of the entire table. And if we used Excel, we would find out that the p-value is actually 0.00008, so very small indeed. And that is Section 3 for Chapter 7.